Okay, this is going to be our second hour on the pumping lemma of regular languages. Let us see a bit more about the implications of the pumping lemma. In particular, we will prove a few other languages as non-regular. So I start with our first example of today. Consider this language L, consisting of strings of the form something like this, and maybe I add some C. That's okay. So some number of A's followed by some number of B's followed by just two C's. This is now actually over A, B, C. Okay, alphabet. And I demand that AM should be greater than equal to N. And I have to show that this language is not regular. In order to do so, I will tell you how to formally write pumping lemma proofs. I do not need to worry about existence of DFA and all that stuff. But thanks to the pumping lemma, that formal statement, I can just start with that K, which is a pumping lemma constant. So prove that this is not regular. Proof. So every pumping lemma proof may start like this. Suppose that L is regular. And then I do not have to talk about the DFA, but I just say let K be a pumping lemma constant for L. This is what actually is given by me by the daemon. But anyway, I do not have to worry about how this K comes from. It's a constant positive integer. Now I choose the language, choose the string alpha, x, y, z with, let's say, x equal to a power n, or k, y equal to b power k, z equal to c square. Okay. This is just to demonstrate that we can have x, y, z non-empty. Okay. This is just for convenience. In particular, what I have, y is number of k's. So k is greater than equal to k. So it is in this language L. So alpha is in L because k is greater than equal to k. And the length of y, the middle part, is k, which is again greater than equal to k. And therefore, I can supply this alpha to the daemon. Okay. And the daemon gives me a decomposition of y. Okay. So y have a decomposition of the form u, v, w such that 1 v is non-empty, Second thing is the total length of u and v is less than equal to k, but this is obvious because y itself is of length k, so this is not important in this exercise. But this string alpha I x u v power I w z is in L for all I greater than equal to 0. Okay. M should be greater than equal to n. So this k is given to me by the daemon. Likewise, this decomposition is given to me by the daemon. Okay. Now I have a choice for I. So take I equal to 2. Then what is V? V is non-empty. It is sitting inside this block b power k. So V must be b power L for some L greater than 0. Okay. But then if I look at alpha 2, this is x a power k. u v w, I have just taken another instance of v pumped in. So this will be of the form b power k plus L c square, because z is just c square. Pumping lemma says this must be in L. But for such a string a power something, b power something, c power something to be L, the number of times a appears must be larger than or equal to the number of times b appears, followed by exactly 2 c's. Okay. In this case, this says that k is greater than equal to k plus L, but that is absurd. Okay. Since L is greater than 0, k is less than k plus L, we have alpha 2 not in L. So this is the contradiction. Alpha 2 is in L, alpha 2 is not in L. Okay. So we do not have to actually talk about a DFA, the repetition of states and all that stuff. We can mechanically use the pumping lemma by first assuming that L is regular and by starting with the pumping lemma constant k. So these first 2 lines should be there in any proof. Okay, we don't have to worry about how this k is coming from. Definitely it's coming from a DFA, but we don't need to worry about it. It's after all a constant. Okay. So let us see a little bit more complicated example. This is our example 2. Consider this language L. Or maybe n factorial, I write. K has some meaning. N factorial. N is greater than equal to 0. This time, this is a language inside the unary, over the unary alphabet A. Okay. I have to show that this is non-regular. Suppose that L is regular, or assume that L is regular, and let K be a pumping lemma constant for L. Okay. Now take, in this example, I will take x equal to z equal to epsilon and y, the middle part, equal to a to the power k factorial. Okay. That is, we have alpha equal to xyz, which is nothing but y itself. This is definitely is in L. Okay. And also the length of y is k factorial, which is greater than equal to k. And therefore, we have a decomposition of the form y equal to uvw such that again the length of v is greater than 0, and definitely the total length of u comma v, uv less than equal to k, but we will not use this in this exercise. And the string alpha I x u v power I w z, x and z are in this case empty, so I can just write it as u v power I w is in L for all I greater than equal to 0. So now the choice of I is little bit tricky. Okay, so take, in this case, this choice of I works. What should I take? Plus 1 or minus 1, plus 1. Okay, k plus 1 factorial plus 1. Now note that v must be of the form a power L for some L in the range. Okay, and in this alpha I have pumped this a power L how many times? K plus 1 factorial times. Okay, and this one stands for the first initial instance of v already sitting inside alpha or alpha 1. So by the pumping lemma, alpha I is in L. And what is the length of alpha I? This will be, here I have k factorial, and I have introduced this a power L, k plus 1 factorial times. Okay, so it will be L times k plus 1 factorial. Okay, and since this is in L, is alpha I, so its length must be of the form, let us say p factorial for some p. And you can see this must be greater than k plus 1. Because L is greater than 0, this is bigger than k plus 1 factorial. So now if I divide throughout by k factorial, what do I get? 1 plus L times k plus 1 k factorial. So I have k plus 1, k plus 2, k plus 3 up to p. Okay, so here this is the trick, choosing some I carefully. Okay, now you see that this is a multiple of k plus 1. This is a multiple of k plus 1 plus 1. So overall this is not a multiple of k plus 1. So this essentially gives me a contradiction, since k plus 1 is at least 2. Okay, something which is a multiple of k plus 1 and not a multiple of k plus 1 simultaneously, this is not possible. So this contradiction proves that L cannot be regular. Okay, so there are several other proofs, but we will study a few in tutorial exercises. So I, for the moment, tell you a trick about what is called using the closure properties of regular languages to prove some non-regularity result. closure properties. So this is important. Okay. So maybe I start with this example first. Maybe something like this. Set of all W in AB star such that the number of A's in W is equal to the number of B's in W. Okay. For example, A, B, B, A, B, epsilon, A, B, 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 A, B, these are all in L. Okay, so it's not of the form A power n, B power n. These A's and B's can be permuted, but the total count of A must be equal to the total count of B in this string. Okay. So of course, I can make a formal pumping lemma proof, but I can also proceed this way. Suppose that L is regular. Now consider this regular expression. This is regular because A star B star is a regular expression. Okay. And we know that regular languages are closed under intersection. So L intersection L A star B star is also regular. Okay. So here I am using closure under intersection of regular languages. But then what is this? If I intersect this language, given language L, with A star B star, we get nothing but the language A power n, B power n, such that n is greater than or equal to 0. And if L, this given language is regular, then this language is also regular. But this is already a contradiction because we have proved that this language is not regular. Okay. So here I am actually not using the formal pumping lemma proof, which can be done in this example, but I am not doing it. But using the closure property and a result, a non-regularity result already proved in order to prove this new language is again not regular. And here I take a second example like L. Maybe this, so I do not have this C square here. Okay. M greater than or equal to n. Just let us take. Okay. This is the first example without C square. The C square actually doesn't matter. Okay. Now, if L is regular, so suppose L is regular, so this implies the reverse of L, strings read backward, so that is of the form B power n, A power m, such that m is greater than or equal to n, is also regular. So here I am using closure under reversal. Okay. But if this language is regular, it has a DFA. So if I interchange the roles played by A and B, the input symbols A and B, then I can say that the language L prime, which is A power n, B power m, m is greater than or equal to n, is also regular. And if I also interchange this n and m, this can also be written as these are all the same language, right? This one and this one. And this one, I have just, from this one, reverse L to L prime, I have just reversed the role of A's and B's, swapped the roles of A's and B's, okay? But then I again use the property of closure under intersection. L is regular, L prime is regular, so the intersection of L and L prime must be regular. But then, what is L intersection L prime? On the one hand, we have a power m b power n, m greater than equal to n. And on the other, we have a power m b power n, m less than equal to n. So this is nothing but a power m b power n. I said both m greater than equal to m and less than equal to n. So m is equal to n, which is nothing but this language. Okay, so this is a contradiction. So given a few non-regularity proofs, I can often use closure properties to prove some other languages to be non-regular. Of course, you can use the original pumping lemma to prove both these languages to be non-regular. So I leave it to you, easy exercises. Prove that these two languages are not regular using the pumping lemma instead of using closure properties. Okay, this is fairly straightforward. Anyway, so I will end this lecture on pumping lemma with a result about ultimate periodicity. This is an interesting result. Let us look at it. Let me give the formal definition first. A subset, let us say S contained in n or n naught, set of all non-negative integers, is called ultimately periodic if there exist constants n0 in n0 and some p in n such that for all n greater than equal to n0, n is in S if and only if n plus p is in S. Okay. So this p is called a period of S. So this means that below this n0, some finite constant, okay, periodicity may be not observed, okay, but beyond a certain finite point, a number is a member of S if and only if the next pth number is again a member of S. Okay. So for example, we may have something like this. 1. Consider this. Maybe start with 0, 1, 4, 8, 10. Here you can see 0 to 1, 1 to 1 plus 3 is 4, 4 plus 4 is 8, 8 plus 2 is 10. But from this point onward, it will be something like 10, 15, 20, 25, 30, 35. Okay. So the implication that all the multiples of 5 will appear after this 40, 45, 50, 55. This is ultimately periodic with period 5. Actually, 5 is a period, 10 is also a period, 20, 15, 1000. These are all periods. Okay. So 20 plus 5, 10 plus 5, and here n0 is 10. Okay. It did not start from the very beginning, but from some point onward, this must happen. Okay. So this is called the initial non-periodic part, aperiodic part, and after that, this is showing full periodicity. Okay. And let us take another example. Maybe this, I have designed this for you, okay. 1, 3, 8. Then starting from 10, you take every third integer, 13, 16, 19, 22, 25, and so on. And also take, maybe I start from 11, and take every second integer, 13, 15, 17, 19, 21, 23, and so on. So this will be in the flattened form, 1, 3, 8, then 10, 11, 13, 15, 16, 17, 19, 21, 22, 23, 25, and so on. This is also ultimately periodic, and you can check with 6 as a period. So 3 is the period here, 2 is the period. So here the period is 3, here the period is 2, and if I take LCM, this is the period 6. And here n0 is again 10. Okay, so here n0 is again 10. So 10 is there, so 16 is there. 11 is there, so 17 is there. 13 is there, 19. 15, 21. Okay, and so on. Okay. So this ultimate periodicity surface in some results pertaining to regular sets. Okay. So here this is an important and interesting theorem. Let L be a language over the unary alphabet A. Okay. Then the set of all M such that A power M is in L. This set is ultimately periodic. Then this is ultimately periodic if and only if L is regular. Okay. Incidentally, I forgot to mention one thing. So I leave it to you as an easy exercise to prove that any finite subset of n or n naught is ultimately periodic. Okay. You prove it. This is fairly straightforward. Something which is vacuously true. So, yeah. So for the sake of, I would say, avoiding the special case, I will assume that this is an infinite set. Okay, but whatever it is, so I will assume that this M is infinite. So once again, I leave it to you in exercise. Handle the case when it's finite. Okay. So I one by one prove this if part and the only if part. Okay. Let again D be a, so if means L is regular. Let D be a DFA with language of T equal to L. Okay. Now, first of all, this is a DFA, so it is deterministic. I have not started with an NFA. I have started with a DFA. Okay. Second, for any state, P of D, this thing delta PA is unique. So starting from a given, starting from any state, if you have some more A to scan, there is a unique state where you can go to. Okay, where this DFAD goes to. Okay, because this is deterministic and the alphabet is unary, only one symbol. Okay, so that means you start from S, read A, read somewhere, read A, read somewhere. Okay, read A, read somewhere, A, read somewhere, you read A, go somewhere. But since this D has only finitely many states, these states is this state, this state, this state, this state, this state, they cannot generate an infinite sequence of different states. So eventually it must happen that some state, okay, will be the same as a state that we have seen earlier. Okay, something like this. Okay, so some state must eventually be repeated. Okay, so now, so that means that once the machine enters this loop, okay, it will keep on evolving in that loop. And you may have some accept states here, here, some here, here, and so on. And then it is easy to see that this thing a power m is in L, okay, is ultimately periodic, where a period P is the length of the loop or cycle, I would say. Okay. So this is one part of it. For the on-leaf part, this is also not so difficult. Okay. So given that this set I think I have written it correctly, yes, is ultimately periodic. Okay, so that means there exists some, okay, maybe some initial part up to n0, some, let us say, m1, m2, up to mr maybe. Then you have something like n0 here, and you have mr plus 1, and if mr plus 1 is there, mr plus 1 plus p, mr plus 1 plus 2p, all these things will be there. Then I may have something like mr plus 2, okay, and if that is there, mr plus 2 plus p, mr plus 2 plus 2p, and so on. So this set must be equal to something like this. Okay. So now if I consider a DFA, okay, so this is 0 start state, this is m1, this is m2, maybe up to mr, and there you just mark mr plus 1, mr plus 2, and so on. So if we have a DFA whose transition diagram is like this, then it is easy to see that this is the DFA D, then the language of D is nothing but this set M. Okay. That's not exactly the case. A power m such that a power m is in L. Okay, this is that thing. It's easy to see that this is nothing but L. Okay, so this is an interesting result, and let us see some immediate applications of this. Okay, say for example you consider this a power n square, n greater than equal to 0. So if I now look at this set n square, such that n is greater than equal to 0, which is nothing but 0, 1, 4, 9, 16, 25, 36, 49, and so on. And this is not ultimately periodic. Okay. And therefore by this previous theorem, this is not regular. But we have proved this using the pumping lemma itself. Well, this is yet another proof that this cannot be regular. And this may be a new language, a power 2 power n greater than or equal to 0. Then what are the powers of 2? So this is nothing but 1, 2, 4, 8, 16, 32, 64. Again, you see the numbers are getting further and further away. So this is also not ultimately periodic. And therefore, this is also not regular. And we have also seen a power n factorial, n greater than or equal to 0. What are the set of n factorial? This is also, you can easily see, this is nothing but 0 factorial is 1, 1 factorial is 1, 2, 6, 24, 120, 720, 4320, whatever. This is also not ultimately periodic because the numbers become further and further away. So this is also not regular. But again, we have already proved this statement using the pumping lemma itself. Okay, so that's a good if and only if condition for regular languages over the unary alphabet. So I may ask the same question. So what about a general alphabet? Okay, sigma, not necessarily unary. Then we can easily see that this theorem is not true. For example, if I consider, okay, so what I am talking about, so let me just say, let's say L is in sigma star, and I am talking about this set, lengths A to be the set of all M in N0 such that M is the length of some string W in L. Okay, so this was the length, this was basically the subset of N0 that we were talking about earlier when our sigma was a unary alphabet, right? So now I am looking at this for a general alphabet, and then I ask the question, L is regular, this is the question, if and only if length A is ultimately periodic. Is this true? Okay, now for one direction, this is certainly not true. For example, if I consider this a power n, b power n, n greater than or equal to 0, this is my this is my L. If L is this, then what is length L? This is nothing but A0, B0, so 0, 2, 4, 6, 8, 10, A5, B5, A6, B6, and so on. This is not only ultimately periodic, it is periodic from the very beginning. But L is not regular. We have proved this. So what about this implication? If L is regular, length A is ultimately periodic. These turns out to be true. So why? So I will give a short proof for this. So L is regular implies lengths of all strings. I do not know why I am time and again writing this as A is ultimately periodic. Okay, so the proof goes something like this. L is regular means L is the language of a DFA. D. Okay. Okay. Now, unlike the case of unary alphabet, a DFA like this may have multiple cycles. For example, this may be my start state A, this may give this cycle, B, somewhere this cycle. There are multiple bifurcations possible. Okay. Because earlier, in the case of unary alphabets, there is a unique branching from every state. Okay, now there are multiple possibilities. Okay, this, and each may, each branching may lead to some kind of loops. And of course, these loops I have shown as non-overlapping. They may also overlap. Okay, so in this case, D may have multiple loops. Okay, given that the size of this input alphabet is greater than or equal to 2. Okay, but what is important in this context is that although this is multiple and maybe very large, the number of loops cannot be infinite. Okay, cannot be infinite, because the machine has only a finite number of states and sigma is also finite. Of course, here I assume that the size of sigma is finite. Okay, this is an important assumption, but by definition, alphabets are finite sets of symbols in any case. So now you can see that length L, I leave it to you. It's an easy exercise. It's just a visualization exercise rather than a formal writing exercise. Is ultimately periodic. With loops. I should better call these cycles. Finite graph has finitely many cycles. Better loop is typically reserved for a different thing. Length is ultimately periodic with periodicity or with a period equal to the LCM of all the cycle lengths. Okay, Now, since there are finitely many cycles, okay, and I take an LCM of all these finitely many positive integers, I still get a finite number, and therefore length of L will be ultimately periodic. Okay, so we just visualize that this is actually the case. In fact, this can be proved by a result which we have not covered in this course. We will not cover also. Can also be proved by a result called homomorphism. Anyway, this proof is also valid, and so this is all cycles. All means only finite, and this LCM is therefore a finite number. Okay. So for unary languages, I can use this result as a necessary and sufficient condition for proving regularity. But for I would say languages over alphabets consisting of more than one symbols, we cannot use this theorem. But this is an interesting thing. And if we eventually see that length of L is not ultimately periodic, then L is definitely not regular. But some non-regular languages also lead to the case when length of L is ultimately periodic. Okay, for example, if I consider this maybe a sample application. Consider this W in AB star such that the number of A in W is square of the number of B's in W. Okay. So if I call this L, what is this set? Length A. This is nothing but n plus n square such that n is greater than or equal to 0. If the number of B's is n, the number of n will be n square. Total length will be n plus n square. Okay. But this is not ultimately periodic. This will imply L is not regular. Okay, so here I would like to stop. We have seen several ways, like using a DFA, which eventually formalizes to something called the pumping lemma. We have also used the closure properties. And also, in certain cases, we can use ultimate periodicity. These are all techniques to prove certain languages are not regular. Good. So we will find or work with several other examples in our tutorial session. So proving non-regularity is an important topic, and I stop at this point. In the next lecture, I will start with a different topic altogether, which is called state minimization of DFS. Okay, so bye.